some operator O acting on some field phi that interacts with gauge field is given by the integral of a characteristic polynomial associated with that operator, truncated at the 2nth term of that polynomial. So you give me some function of omega that is associated with this operator. That's one example for the Dirac operator. If you give me that, I've got some horrible function, but I'll expand it as a series. The 2nth term in the series, in other words, the form in the series that saturates the dimensionality of the manifold, you integrate that, and that turns out to be the index associated with that operator. So I think maybe I was hoping to finish this off today, but there was a bit more time and the effective stuff than I thought there would be. So if you would you want me to spend the first half hour on Monday finishing this off? Because it's like you don't want to keep you hanging. But we'll get to instantons next week for sure on Monday. So I'll spend the first part finishing off this. Yeah. It means this operator is that operator. So in other words, this polynomial will be associated with this operator in a way that I have not had time to flesh out because we're out of time. So that's what I want to do on Monday. In the case of the Dirac operator, I would write P of D slash of F was trace of F to the S, right? So that, in the case of what we've been doing all along, O is the D slash operator, F is the gauge strength, and it turns out this is equal to that. So all that this subscript means is this polynomial has to be meaningfully associated with this operator O. I mean, I can construct other gauge polynomials of the field strength, but they're not necessarily associated with the anomaly. That P is a special case of the P over there, yes. It is. Well, no, it's not any polynomial function. It is a particular polynomial function that is associated with this operator in a way I haven't had time to spell out yet. That's the whole point of studying this for Monday. So how it's associated with it, I'll give some examples of that. But in some sense, the object of the game, looking at it from this viewpoint, is if you give me an operator, an elliptic operator, and a manifold on which I can meaningfully define a left-handed and right-handed field on which that operator acts, that index will be index of that operator will be associated with some particular polynomial that has to be specified according to the properties of the operator. So, as I say, I jumped ahead about a page just to show you the bottom line, but I haven't. I mean, if you gave me another half hour, I'd do it, but we'll do it on Monday. Okay. Define this quantity omega t to be this, where omega t is equal to omega naught plus t of omega 1 minus omega naught. So omega t interpolates between two connections where t is a parameter that goes from 0 to 1. Then one can show that d by dt of a characteristic polynomial of degree m is equal to m times d of the symmetry of omega 1 minus omega naught of omega t to the m minus 1. And this thing I can call Q of 2m minus 1. And it will depend on omega and omega t. So I can choose omega naught equals 0 for simplicity. What I showed last time, actually maybe I want to do that next. So I showed before that the characteristic class is a topological invariant in the sense that the integral of omega 0 over a manifold is the integral to omega 1 over a manifold. The difference between, it's found by integrating this equation, and the difference between them is the two Q's, but by Stokes' theorem, that will vanish. So the integral of over m of p of omega is a topological invariant, and one can rewrite this thing. This is called the Chern-Simons form. And it, Q2m minus 1 is equal to the integral of m over t, or m times the integral, sorry, of dt, of the symmetry of omega with this curvature to the m minus 1. So it's a generalization of what we looked at last week. And one can show that the variation of this object, the gauge variation of this object, is equal to m times m plus 1 times this integral here. The symmetry of D of that thing, and we could call this thing here the Q2m minus 2. So I'll call this Q1 as 2m minus 2 of delta omega omega sig omega. So that generalizes the non-abelian anomaly we had last time. So this is kind of like the abelian anomaly was a special case of this, and the non-abelian anomaly was a special case of that. And the index theorem, yep. Well, in other words, how do we know what it is? Or, okay, it is some polynomial in the curvature that I have not defined, except to say that it is a polynomial. So here,